Hello and welcome to another Smart Grid System class. Before I start the class, I want to give an update on your final project and also your final exam. Um, for the final project, I have decided to give an extension until May 10th. So if you have any questions about your final project, just please let me know. I will also post an announcement about this extension of your final project. And for your final exam, it's going to be everything that we covered in the class. It's going to be a comprehensive exam. And I'll give more explanation in the next class about your final project, final exam as well. So today's class, the smart grid system, we want to speak about energy storage, which is a very important part of any modern smart grids. So what is the energy storage? Energy storage, obviously, you can capture the energy produced at one time and release the energy for use at a later time. We usually it involves the energy conversion from one form to another. So it could be electrical to mechanical and back from mechanical to electrical, or it could be thermal, or it could be chemical energy like a battery. So today's class will be focused on electrical energy storage. So for the first question is, why do we need energy storage and why is it important for a power grid? There are several reasons. Some of the reasons are to mitigate net load fluctuation, to maintain power balance between supply and demand, for peak shaving, cost reduction, provide fast frequency support, and because of the rise of the renewable energy, we face a lot of new challenges. Uh, like solar energy produces a lot of energy during uh, day, but at night when we need it, it doesn't produce any energy. So we wanted to shift that energy and store that energy to be able to use it later in the day and at night. And it's also the same for wind. Sometimes the wind doesn't blow, so you need to have a backup. And nowadays, energy storage systems, especially the chemical batteries, lithium ion batteries, have gone relatively inexpensive, and they actually compete with fossil fuel uh, energy systems, power generator systems like natural gas and coal. Different type of energy storage. We have the ultra capacitors or supercapacitors, batteries, flywheels, pumps stored hydroelectricity, compressed air, thermal energy, gravity base, etc., and even hydrogen base and so on. The key parameters of energy storage systems are that the power capacity is usually measured in megawatt or kilowatt, and the maximum stable power that can be produced on a continuous basis is the power capacity. It's called the power capacity. The energy capacity is the power produced per hour. So imagine you have a tank, a reservoir, water tank. The total amount of water that you can store in that. So if it's like 10,000 gallons or 20,000 gallons, that's going to be your capacity. And in electricity, we measure it in megawatt hours or kilowatt hours. So it's the total amount of energy that can be stored or discharged, and it's measured in megawatt hours and kilowatt hours. And also the state of charge, which again, it's a percentage number. Like if it's 50, 60, same thing that you have the charge on your phone and so on. Describes the current energy level of energy storage. It is a ratio of the current stored energy to its energy capacity. And finally, we have duration, which is the ratio of its energy capacity to its power capacity. This graph shows the energy storage and with two graphs, the duration and also the power capacity. So some energy storage systems have a shorter duration, like high power supercapacitors. They can only hold energy for small for a small time, for a short time, um, because it's going to discharge. So a supercapacitor and a capacitor in general, it's not like a lithium-ion battery. It could store power for a few seconds maximum, and it's going to auto discharge. Um, so they are not good if you want to store energy for a long period, like for a day or 2 hours or 3 hours. But they're very good if you want to regulate the power, you want to flatten the curve, you want to provide frequency support. Um, this is a good solution because it could store energy very fast and it could discharge very fast. So the supercapacitors, uh, superconductive magnetic energy storage is. Then we have the flywheels. Then we have the nickel metal hybrid batteries, which again in seconds and minutes, and then different type of batteries. And if we want to store it in hours, it's going to be flow batteries, sodium, sulfur batteries, hydrogen, and fuel cell. And for the power capacity, again, the capacitors are usually low power capacity. For very high power capacity, we have pumped hydropower storage, compressed air, hydrogen related, mechanical, mechanical, and electrical are the different types, which are color coded here. I forgot to mention this. So mechanicals are the red ones, electricals are the green ones, and uh, electrochemicals are the blue ones, which are the batteries, are batteries. So you can see that ultra high power capacities are the hydro pumps, and they can store energy. The duration is pretty long. You can store energy in a hydropower system, um, a dam for hours and months and so on. But they are pretty slow to deploy, by the way. It takes few hours sometimes to get the energy back. This is a graph that shows energy storage. You can see that uh, it's about 50-50 right now. Um, this is an older graph, but it shows most of the energy almost comes from hydro systems like the dams that pump the water up. And I mentioned this in the previous class, the hydro storage. And the other half comes from non-hydro, which the majority of that is lithium-ion batteries. As you can see, compressed air flywheels have a very small percentage of that. This is another graph which shows the energy storage set for decades of growth. And this is the global energy storage. Right now is around 100 gigawatt. And it's projected to reach 230 gigawatts in 2035. And you can see the blue color is the US. And the majority of that is in China right now. Yeah. So these are some numbers from March 2018. The electrical energy storage installed was 25.2 gigawatts. 94% is pumped hydroelectric storage, most of which were installed before 1980s. And the battery accounted for 733 megawatts, which most of them were lithium ion. The thermal storage accounts for 669 megawatts, and compressed air was 114 megawatts, and flywheels was 558 megawatts. This was 7 years ago. Now let's see what happened since. This is only the battery capacity, which has increased 66% in 2024 alone. And I'll show you more interesting graph. So only the battery capacity has grown to 26 gigawatts. Back then, it was just 733 megawatts. So the battery capacity alone has exceeded the total storage install capacity by 2024. And it's projected to just explode. The main reason is the batteries have become uh, very cheap in the past 7 years. So now let's speak about different technologies of stored energy systems. We have the flywheel energy system or storage, which is a mechanical device, a high-speed wheel, a rotor, rotates around an axis and stores energy mechanically in the form of rotational energy. In the charge mode, it uses electricity to accelerate a flywheel, which converts electric energy into kinetic energy. In discharge mode, the spinning force of the flywheel is used to turn a generator. Flywheel will decelerate. Usually the motor and generator is the same. We use a single motor generator, and it acts like a motor when you give it electricity provided with electrical energy. And when you cut the power, the flywheel is gonna turn the motor and act like a generator. To change a flywheel stored energy is to increase or decrease its rotational speed. Flywheel stored energy in proportional to square of its rotational speed. And it could go up to 60,000 revolutions per minute. They're using now magnetic bearings to be able to achieve that high speed. Now, this is an example of, you can see here a flywheel energy storage. Again, we have a bidirectional converter. This acts like a motor and generator. We have a thrust bearing, the radial bearing, and a vacuum pump, and the flywheel rotor, which is a big mass of very heavy mass. And usually we use vacuum pump to reduce friction and increase efficiency. We also use magnetic bearings as well. As you can see here, this is another example using magnetic bearings in a vacuum enclosure to reduce friction. So these are small storage facilities with high output power. They have long lifetimes, decades with little or no maintenance. Their application is to maintain a grid frequency, so for short periods of times to be able to also mitigate short-term net load fluctuations as well. Another type of storage system is the compressed air energy. It works the same as a hydro energy. So we have the pumping mode, which compresses air into a cave cavern using the motors and pumps. Usually we use like decommissioned gas wells or other type of wells, or if there's a cave left behind from mining, we can use that. And then we have the generating mode, which it's the pressurized air is then released through a turbine to generate electricity. The cons of the systems are it's limited by geography, as it requires big caverns because we don't have a lot of them. And the features are smaller to pump hydraulic storage, but instead of pumping water, it pumps air. So one thing to keep in mind for compressed air energy is that it has several problems. First of all, because we are converting electrical to mechanical energy, and then combining, and then again, converting that mechanical energy, which is a turbine, to electrical, you have a loss in the compressor and generator, especially these compressors get very hot. And the other problem is the leakage that you have. Obviously, these Caverns have a lot of cracks and sometimes the air may escape. So it's not very efficient. And this is another way to compress air is to use wells. Uh, and again, it has the same problems. And I've mentioned here an example of this type of stored energy. So it has its own drawbacks. Efficiency is usually below 60%. Another type of energy storage is the gravity. It uses gravitational potential to be able to produce energy using the potential energy. Uh, it has two modes. We have charging and discharging. In charging, it consumes electricity to lift a heavyweight object higher off the ground. And then in discharging, we lower that heavy object to convert potential energy into electric energy. There are two types. We have the vertical movement, and then we have the rail-based, which is a rail system on a slope, and the vertical movement is usually a building-based energy storage system. This type of system, this is actually being built in China. It's a 10 megawatt system, 10 megawatt hour. And the problem with this, it requires a lot of upfront costs. The CapEx, the capital cost is huge usually. It requires a very large infrastructure. But the benefit is it's going to last for 20, 30 years. This is another example of a gravity energy storage system in Switzerland. This is a commercial scale system as a grid energy storage. It lifts and lowers some bricks. It was completed in 2020. This is an example of rail-based gravity. Again, you have a slope. In charging, you have a motor, a winch system that pulls the cars up. And when you want to discharge it, you just leave it to go down, and it's going to turn the motor, which now it's going to act like a generator and produce electricity. So fully charge the mass car at maximum elevation, resulting in maximum potential energy. And in discharging, the mass car is load to turn the reversible motor backwards and acting as a generator of power. One system has been built in Nevada. It's developing a 50 megawatt energy storage facility, approximately 20 acres at Gamburn Pit. It employs a fleet of 210 mass cars weighing a combined 75,000 tons. The good thing is you can use decommissioned rail cars. It's operating on a closed set of 10 multi-rail tracks. It aims to provide ancillary service as regulations resources for California. Another type of energy storage is thermal energy storage, which has become very popular lately. This uses excessive electricity to produce thermal energy when demand is low. It can store thermal energy for use for hours, days, or months later. It has two modes. We have pumping mode and generating mode. Pumping, it consumes electricity to produce thermal energy. And in generating mode, it uses that thermal energy to either generate electricity or directly meet thermal demands. So if you want to generate electricity with that, or you run water, and it's going to evaporate that water, turn a turbine, and generate electricity. It's widely used in concentrating solar powers systems because they directly, their output is thermal energy, so it can directly give that thermal energy to these thermal energy storage system and store it and use it later on. Examples of concentrating solar powers with thermal energy storage. So as mentioned, you have a liquid running in to the tower, it heats up, and then you have it in the hot storage tank. And if you want, you can generate steam with that. and produce electricity and then pump the cooled water back or cooled liquid back to the system. In these heat or thermal energy systems, they use sand or some type of bricks that have a very good thermal storage capacity. This is an example of a thermal energy storage, which is a temporary storage of energy by heating or cooling the energy storage medium. We can use different sources of energy, solar, electricity, industrial heat, to heat up the system. Here could be, so this is a sulfur-based TES system, and then we can convert it back to electricity, or we can use it as heat, as a heat source. And finally, the most popular one that has become very popular in the recent years because of the advancements in battery technology and reduction of the cost because of the mass scales, and because they're shared in the automotive industry, the price has reduced significantly. So the batteries store energy in the form of chemical energy. The most popular type is the lithium-ion battery. It's most widely used. 80% of large-scale battery storage are using lithium-ion. They have high energy density, low self-discharge. They contain a flammable electrolyte and may be kept pressurized because of the fire risks. It uses the lithium ions as charge carriers. We also have different type of other type of batteries like sodium ion batteries, which just recently CATL announced they are putting sodium ion batteries in the new EVs. They have developed a type of sodium ion battery. Sodium is much more abundant than lithium, so it's going to create a cheaper, much cheaper battery. They usually cost a 30-40% cost, but the battery density of sodium ion is also lower than lithium ion. And the newer technologies are the solid state batteries, which use silicon as electrolyte. So, but they have not been mass produced yet. They are difficult to mass produce. And we also have flow batteries. These are liquid batteries. They have long cycle life, quick response time, and safe, but they have low energy density and they are high cost. The principles of a lithium ion battery, we have the discharge mode, which, as you can see, we have an anode, as you know, and we have a cathode. The lithium ions move from the negative electrode through an electrolyte to the positive electrode. And this is when we are discharging, and when we are charging, lithium ions move from the positive electrode through an electrolyte to the negative. This is a small typo. So we have high energy density. Lithium ion is about 100 to 265 watt hours per kilogram. Lead acid is 35 to 40. So 5 to 6 times less. They are low self-discharge, 0.35% to 2.5% per month. It's very low. You just leave it there for a month. It's just going to drain for 2% maximum. You have low memory effect. The memory effect is the battery appears to remember the smaller capacity. The newer batteries charge cycle for lithium iron phosphate, the iron phosphate batteries, the charge cycle is much higher, up to 5,000 cycles, which far exceeds the vehicle life. And also they are much safer. They won't catch fire. They're almost impossible to catch fire, the newer generation. They are lower in energy density to lithium cobalt on nickel, lithium ion, but they are much safer and have a much higher longer lifespan. These are the battery energy storage by 2017. I've just mentioned this in the progress that has been made. And you can see that by region, and this was in 2017. For ERCOT, it was 83 megawatts. CA, the California's CAISO was 130 megawatts. And this was the large-scale battery storage capacity by region in 2012. You can see just there was a couple of them in California, Texas, so on. By 2018, that grew exponentially. But you can see a lot of states added large-scale battery storage. And just in 6 years after that, actually 5 years after that, 2018, you can see that it exploded. And you can see that the Three Rivers Energy Center now generates 1.2 gigawatts. It has 1.2 gigawatts of energy storage. I'm sorry now. Yeah. Oh, this is not the, just disregard that one. I've added the wrong graph. But yeah, I will show you another graph that I shared before. So let's delete this one. Yeah, I wanted to show this graph here. This there was 1.5 gigawatt operating battery power capacity in the US by 2020. 71% was standalone. It was projected to increase by 14.5 gigawatts in 21 to 24. But what happened was instead of 14.1, it went by 26 to 26 gigawatts. And in 2024 alone, it increased by 66%. Again, main reason is that lithium iron phosphate battery, which have become very, very cheap. And the capacity actually surpassed the predictions much more than it was anticipated. So some battery power plants, we have the Slate project by Goldman Sachs Renewable Power, plus the battery storage in Kings County, California's solar power is 300 megawatts, and the battery is 140.25 megawatts or 561 megawatt hours. The project was first announced in October of 2018, and the construction began in January 2021. And this is the battery power plant. Other storage plus solar projects, we have the Edward Sanborn solar storage, which is 1,000 megawatt solar PV or 2,000 megawatt hour battery, built in phases in Kern County, California. When it's completed, it will be the largest solar plus battery power plant. The Lilly Solar Plus storage project, 181 megawatt, and starts of construction is July 2020. The operation started in December 21. It's located in east of Dallas, and it annually produces 367 gigawatt hours and reduces 242,000 tons of CO2 emissions. So again, this is the Lilly Solar Plus storage project. You can see. Again, it's in east of Dallas, combination of solar and you have the stored energy. Now let's speak about the energy storage model, the efficiency of energy storage. The compressed air energy storage, as mentioned, is 60 to 90%. Lithium ion energy battery is 90%. For example, the Tesla Powerwall, the 13.1 kilowatt hour one, has a round trip efficiency of 90%. The Tesla Power Pack, or the 210 kilowatt hour, has a round trip efficiency of 88 to 89%. The lead acid battery has the 50 to 95% efficiency. Pump storage hydro is 70 to 80. And fuel cell is 40 to 60. So you can see the best efficiency is lithium ion batteries. Does have any mechanical parts. So less maintenance. And also now it's become even cheaper than any mechanical based storage system. If it becomes like 30 or 40% cheaper, it's going to replace all the other energy storage systems. So for energy storage model, we have generic energy storage model. The variables are the charging, discharging status, the binary variables. We have the charging, discharging rate, power, the continuous variables, and we have the energy level, which are continuous variables. And these are the notations. UC as 1 indicates charging mode, otherwise 0. UD indicates 1 indicates discharging mode, otherwise it's 0. PLC is energy storage charge rate. PD is the energy storage discharge rate, and E is the energy storage energy level. The energy storage systems have an energy capacity limit. So the capacity limit is between 0 and the maximum. The reduced limits for some energy storage, such as batteries, we have the SOC minimum, which is a minimal level for the state of charge percentage, and SOC maximum is the maximum level for state of charge percent. Some batteries, they're going to be very unstable if you charge them over like 90-95%. So we want to keep the charge level usually between 20 and 80%, which is the optimal level. We don't want to reduce below 20% and increase it over 80% because it's going to shorten the lifespan. So since the lifespan will be significantly shortened if 100% of energy is used up, again, we want to use that ideally between 20 and 80%. And most time it will be used only between 30 and 60% or 30 and 70%. The SOC is the state of charge, which is the ratio of current stored energy to its energy capacity. And we have the DOD, which is the depth of discharge. An alternate term to indicate SOC describes how deeply the battery is discharged in relation to its total capacity. So if the battery is charged and discharged between 20 and 80%, it's going to last, like, for example, 5 or 10 years. But if it's charged from 0 to 100% back to 0, it's just going to last a couple of years. So we have these BMS system, battery management systems, that are able actually to, for example, stop charging when the charging reaches 80% to protect the life of the battery and extend the life of the battery. The batteries are SOH, which is another indicator. It's a figure of merit that measures the general condition of the battery. On your iPhone, if you go to the settings and general and then battery, the battery health, you can see the battery state of health. If it says like 90%, means the battery's health is 90% of the original battery when it was first produced and it was new. If it's under 85 or something, it's probably the time to change the battery. So again, this is the ratio of updated capacity to the original capacity of a fresh battery. The state of battery will be 100% for brand new batteries, and SOH gradually drops over time. For an EV, newer technology, because they have battery management systems and cooling systems, usually they use 1 to 3% of their battery full capacity per year. For a smartphone, it's a little higher than that because smartphones get hot and they don't have a cooling system. So it's usually sometimes 4-5% a year. And after usually 3 or 4 years, you need to change the battery. The energy capacity limit for degraded battery, E is between 0 and the state of health of the battery times E max, or 0, but it's E between 0 and E new max. This cycle is another parameter, which is one loop of charge and discharge. And the cycle life is the number of complete charge discharge cycles before the SOH drops to a specific level. Example 80%. For older generation battery, it was like 500 cycles. From 24, I think 2024, for example, the batteries new in the new Apples, they are increased to 1,000 cycles, if I'm not wrong. Yeah. For the new EVs, it has even for some EV batteries, it's increased to 5,000 cycles. And imagine if you want to charge it once a day and you're not charging it actually from 20 to 80%. Most times in the day, you're charging like 15 or 20%, just between like 40 and 60%. And when we speak about cycle, it's like usually a full cycle. So it's going to easily outlast the vehicle. The other components will probably fail sooner than the battery. So you're gonna have 5,000 cycles at least. If you want to charge it once a day, it's gonna be at least 20 years. The number of complete charge discharge cycles before the SOH drops to a specific level. By the way, this is for the state-of-the-art new batteries. Older car batteries, they are around 1,000 cycles. They can easily last between 6 and 10 years. Most manufacturers right now are offering warranties for 8 years and 150,000 miles. So they're pretty sure it's going to hold up for that amount. And that is like 90% life cycle. If it drops below 90%, they will change the battery. So the life cycle is the number of complete charge discharge cycles before the SOH drops to a specific level. For example, 80%. For this one, it's 10,000. From 10,000 life cycles, it goes. You can see the DOD here, which is the depth of discharge. You can see that the lower if the depth of discharge is, it's going to have a higher life cycle, meaning instead of going from 20 to 80% charging, you can do just between 40 and 60. It's going to substantially increase the lifespan. And it's not like after the life cycle is over, you need to throw out the battery. Now there are a lot of companies that take out the batteries, like from the early Teslas and Leaf, and they use them as the storage of a grid storage energy storage system, because the power density is lower. They still have like 60-70% of their life cycle left, and they could be used another 10-20 years for power grid. If it's still like not deformed or hasn't been an accident, it could be perfectly used for another 20 years for stationary energy storage model systems. The energy storage model, we have some constraints. The unit cannot be charged or discharged at the same time. Limits on the charging rate and discharging rate. We have ramping limit, change in charging rate and discharging rate. We can't charge it immediately from 0 to 100%, obviously. And we can't discharge it fast because it's going to damage the battery. And we have energy capacity limit as well. And these are the limits that we have for ramping limit, for charge and discharge rate, and so on. This is a energy storage model, and this equation shows the energy storage efficiency. And we can see that sometimes it shows mu C or eta C is the charging efficiency percentage number, and mu D is the discharge efficiency percentage number. Delta T is the length of the time interval. And we have these equations for, again, for storage efficiency. And in the graph, you can see we have the ideal energy storage. We have some losses, and then it's going to be connected to a power grid. And the question here is, can this model represent pumped storage hydro? The PSH may have 2 reservoirs, while this model is for energy storage with only one single reservoir. So We already went through this model. This is a mathematical model for pumped storage hydroelectricity. This is equation for the generating mode and the pumping mode. This is just for your knowledge. You don't, again, need to memorize any of these. And we already went through this and how it generates power, and depends on different parameters like the head and the height of the dam, and also amount of water that we have, and so on. So the energy storage efficiency is showed with this equation, which shows the charging efficiency, the percentage number, and the discharging, the charging efficiency and the discharging efficiency. And this shows the round trip efficiency, which is again, all of them in percentage number. So round trip efficiency is the ratio of the amount of energy that can be used to the amount of energy that it took to store it. It is expressed in percentage. After this discharge efficiency is removed and combined with charging efficiency, the energy equation becomes like this. As I mentioned, for example, some energy storage efficiencies were mentioned, I think, here. For battery, lithium-ion battery, like Tesla battery is 90%, lead acid battery is 50 to 95, compressor is actually closer to 60 to 70%, and pump storage is 70 to 80, and fuel cell is 40 to 6. That's it for today's class. Thank you so much, and let me know if you have any questions from today's lecture. Have a great weekend.